Hello, and welcome everyone to our webinar Unseen Ease, Efficiency, and Scale in RF Simulations. First off, I want to say that this webinar is being recorded, and all of the registrants will receive this recording after the event. So, my name is Jukka Knutinen, and I'm the head of marketing here at Quanscient, where we have a cloud-based FEM multiphysics simulation software. More about that later. Now, before going into the actual topic of the day, let's go through the agenda of what we have planned here. So we have 60 minutes, and after these welcome words and actually going through the agenda, we'll dive straight into the challenges faced with simulations in RF design. After that, we're going to look at how cloud-based software addresses these challenges directly, and also look at some other benefits cloud-based solutions are already delivering, and of course, examine their real business impact. After that, I'll pass the mic to our technical speaker of today, our CTO and co-founder, Dr. Alexander Hallbach, and he'll show what a cloud-based multiphysics simulation software actually looks like and what it's like to actually run simulations with one. Dr. Hallbach will cover a few different use cases to, one, demonstrate the basic functionalities of importing GDS files, defining materials, and setting up physics, but most importantly, show where and how the actual magic happens. So how you can simplify the setup through various features and run hundreds or even thousands of simulations in parallel with zero added computational time. So indeed, we'll take a look at some parametric sweeps our customers are using for design optimization and the results from these live runs. After the demo section, we'll have a Q&A with the questions you have submitted beforehand and end with some finishing thoughts and instructions on how to get started with a 7-day free trial of Quanscient Allsolve. But without further ado, let's dive right into challenges faced in RF simulations. So to set the stage, I'm going to assume most people here in the audience are not using cloud-based simulation software, but rather have their tools running on their desktops or workstations. So basically their own hardware. Well, many are already switching to cloud-based tools. This still seems to be the case predominantly. And as such, the first challenge is the limited computational resources, which are limiting design exploration. So indeed, as stated, most people are still running their simulations with their own hardware, meaning that however powerful the machines might be, there is still limited access, if any, to truly high performance computing resources. What this means in practice is that if you want to perform, for example, sweeps to test different parameters for simulations, they would have to be run sequentially. This, in turn, simply limits the number of design variations you can realistically explore within a given time frame. This then leads to, in the end, suboptimal products and possibly missed opportunities for innovations, just to name a couple. So that's one thing. The other is that with this legacy software, even if you had unlimited access to on-premise clusters, traditional RF simulation tools have restrictive licensing structures, limiting the number of concurrent users and therefore simulations. So basically, running hundreds or thousands of simulations in parallel would be exceedingly expensive, even if you had the computing power at hand. The limited number of software licenses can also create bottlenecks for teams, especially in larger organizations, making it difficult to scale the resources as these projects grow. Finally, many RF simulations tend to be tricky to set up and require quite extensive knowledge of the software. Many of you in the audience might know your tools like the back of your hands, but not everyone is so experienced. And especially in the beginning, simply learning to use the tools efficiently to set up the simulation can be time consuming and therefore expensive for the companies. And as always, with anything complex, errors or at the very least inefficiencies are prone to happen. So then, how are cloud-based software, namely Quanscient Allsolve, addressing these issues? Well, let's go through them one by one. For one, the practically unlimited computational resources enabled by cloud computing allow for expansive design exploration. So indeed, Cloud-based software provides on-demand access to virtually unlimited computational resources, which allows engineers to explore a wider range of design variations without hardware constraints. This can then lead to more innovative and optimized RF designs and a competitive advantage through faster time to market and overall superior product performance. Next, there's the enhanced collaboration and scalability provided by the flexible licensing. So, for example, with Quanscient also, well, you can say that there is an unlimited number of licenses, or simply that there aren't any licenses whatsoever. So, how it works is when a company or an organization purchases a plan, everyone in the organization can be given access to the platform to view and or edit the projects. So naturally, this makes collaboration easier when you don't have to have anything downloaded on your computer to view the projects or results, and you never have to worry about any seats on the software. Furthermore, as there is an unlimited number of licenses, there isn't a limit on the number of concurrent users or simulations you can run in parallel. So, in part, it is the licensing model that allows for the hundreds or thousands of parallel simulations, along with the practically unlimited computational power from the cloud, of course. So, indeed, this allows teams to very easily scale the software resources as needed, both up and down, as the number of seats will never become a bottleneck or incur any additional costs. Finally, the cloud platform provides secure storage for the projects, which are accessible on any device from any location, and again can be easily shared and accessed within the organization, similar to any other cloud-based storage such as Google Drive or OneDrive. Then there's the simulation setups themselves. Now, I don't think it makes much sense for me to talk about this much, as Dr. Halbach will in just a moment show it to you live. What I can say is that through the intuitive GUI and certain other features, setting up these complex RF simulations for hanger resonators, antennas, RF filters is easier and indeed does increase the productivity and decrease the onboarding time for new hires. But as said, we'll get to see a thorough live demonstration, or actually a few of them, in just a few minutes. But before that, let's quickly cover some of the other benefits of cloud-based software, and again, specifically Quanscient also. So I'll start with the Python scripting interface, since that has been getting a lot of love from our customers. So basically what we have is a very easily accessible scripting interface with an automatically generated Python script defining the entire simulation setup. We have extensive library of pre-built multiphysics scripts, and you can even extend the physics capabilities for any physics that might not be supported directly in the GUI. So basically, for anyone proficient with Python, the scripting interface allows for maximum flexibility, control, and customization. I'm also sure that we'll see the scripting interface in action in at least one of today's demos. Let's see. Next up, we have the lack of hardware costs and maintenance. So yeah, as everything is browser-based, even the most heaviest and hardcore simulations can be run on a laptop, which means that for a startup, for example, adopting a tool like this can save tens of thousands of dollars in mere hardware costs alone, as there is no need to invest heavily in their own hardware. Yeah, imagine how easy it would be for new hires, for example, to simply buy them decent laptops and they'd be set. No hardware investments or no license fees. So talk about cost savings and a simplified IT structure. But if there's one thing our customers love more than the scripting interface, it would have to be our customer support. So yeah, the support window is just right in there, one click away in the GUI, and it connects straight to our team of application engineers who will, and trust me on this, go above and beyond to make sure that whatever issues you're facing gets resolved fast. So no outsourced support and fast personalized help. In addition to that, we of course have tutorial videos, written tutorials, documentation, and user guides, which are also growing on a weekly basis. Now, a few words on data security and actually data in general. So, compared to storing data in-house, big cloud computing providers such as AWS that we use actually provide more secure data storage in many cases. This is largely due to them investing billions of dollars, so that's billion with a B, every year in cybersecurity alone to just to build and maintain the security infrastructure. Also, with the data stored securely in their servers, encrypted in transit and at rest, they are secure from any unexpected data loss, hardware failures, or even disasters that might occur at on premise servers or let alone some individual workstations. Regarding the security in general, we're SOC 2 certified and working towards the ISO 27001, which is why our public customers such as Infineon Technologies and the United Kingdom Atomic Energy Authority trust us with their simulations. Even further, for our enterprise customers, we're happy to set up private cloud setups, meaning that all the data will be at your own AWS instance, giving you the full control over the architecture and having the data stored in your account. Lastly, there is the advantage of pretty much any SaaS platform, which is automatic software updates and access to the latest features. So we do updates every 2 weeks, meaning that all of our users will always have the most up to date version with the latest features and bug fixes. All right. But that concludes the theory section of our webinar today, which means that it is time to get into the actual stake. So, without further ado, I'll give the stage to our CTO and co founder, Dr. Alexander Halbach, who will now show you how a cloud based multiphysics simulation software, how it actually works, and how it indeed allows for unseen ease, efficiency, and scale in RF simulations. Go ahead, Alex.
Thank you, Jukka. After this nice introduction theory to electromagnetics, I think it's time to dive into as much live demos as possible. So what we're going to do is we will do a live demo. We'll start with a very simple, and then we'll go a bit more complicated. We will have more RF webinars coming. And if there's one thing that I've always missed in webinars is that people go complicated and you go out without really understanding how you're going to set up the basics. And so we're going to fix this by addressing the basics first. So what we will do is we'll go with the most simple possible microstrip simulation with first a wave port setup, which we call eigenmode port, and S parameter calculations. We'll visualize that. Next we will connect a lumped resistor to also highlight our lumped port capabilities and how they might in some situations be more accurate than the classical lumped ports. And then we'll go into a bit multiphysics simulations and we'll investigate how much this microstrip heats up. And then after this, so these three will be live. After this, we'll be going to a hanger resonator simulation. So these are devices used in, for example, quantum computing, superconducting chips, because they have, they filter signal. And we will see how to compute S parameters there, and also how these devices can heat up due to dielectric losses. This one will not be set up live, just because we're going to have a limited amount of times, but I will run it live and we'll see the results. So as Jukka, you mentioned, indeed, it is a browser-based interface, nothing to install. You have all the conveniences, such as sharing the project, just sharing, putting the name, giving access, and sending a link. So no need to juggle between data and send large data files. You also have access immediately in the browser to a bunch and a wide range of demos. Some of them are actually, some we will cover now, of all sorts of multiphysics simulation. So today it's only about RF, but we do all sorts of multiphysics simulation. And you also have access to the support right here. And actually, if you give us access to the projects, and this is upon your decision, we can actually even help you live on your own setup. So like the support is really optimized and really streamlined in a way that's really helpful for you. So no need to send big data files and wait for a response and communicate missing data pieces. But that being said, let's start right away with the very simple first microstrip simulation. So you create a new project in your browser, works on any platform, don't have to install anything. And then you can either import a step file, and this is what we have done with the hanger resonator. You can also import GDS files, typically used in the semiconductor industry. You can actually also even import mesh files as such and proceed as if they were step files. So here we're going to simply draw the geometry. A microstrip is, in the end, a very simple device. So we can just draw 3 boxes. And this is what we're going to do. So the size in the X direction will be 8.65 millimeters. In the Y direction will be 10 millimeters. And in the Z direction, it will be 0.5 millimeters. And this will give us our first box. And I hope my internet is going to be good enough today. Let me draw the next box. Maybe I will switch off my camera. Sorry for this. So the next box will be, so this was the bottom substrate region. I will draw another box, which is the track region. So for that, I could just copy this box. And the track region will be the same, but it will be less wide. So it will be just 0.43 millimeter. These dimensions are all taken from an online reference benchmark. So this is the reason why we consider these dimensions. And the last box is the air on top, which is simply, I could just copy the substrate, and then I can just shift the substrate up. Yes. So the shift amount will be simply like enough so that it's sitting on top of the electric. And I will make it a bit thicker so that you capture really nicely the electric field all around. I'm really sorry for this connectivity issue. Yuka, can you still hear me? I think things are working better now. Okay, all right. Sorry for this intermezzo. So we have our geometry here. Simply a track. We'll be able to access the track. It's a perfect conductor phase here. So you could take the volume into account, but here, just a phase. And what we're going to do now, we're going to assign material to this. So the geometry is now set up. We can assign materials. So we're going to assign, so we have a bunch of predefined materials. We're going to assign an air material. And it seems I will be plagued by internet connection for a longer period. All right, so the air material, it's the volume on top. So I just select this volume at the top, and all the properties are predefined. So you can tune them the way you want. Don't have to do it here. And then we can move on to the other material. So here, no copper material because it's a perfect conductor surface. The other material in the reference that we're following here is simply, it's simply, well, it's not a known material. It's a dielectric material with a given property. So this will help us introduce how to set up new material. So here I select the new material, and I call it dielectric for convenience. And then I can demonstrate this, like how to set up new material properties if we don't have already predefined materials. So let's go to the properties. What I will need here is the electric permittivity, the magnetic permeability, And since I will also run a thermal analysis, I will have to provide the thermal conductivity and the likes as well. Let's start with the permittivity. So here the reference has 10 relative permittivity. So in absolute numbers, so here in farads per meter, 10 epsilon 0, and the magnetic permeability will be mu 0. Now we will also have to provide for a later analysis, thermal analysis. We will also need the density, the electric conductivity, and the thermal conductivity. So here I just take regular PCB material properties, but typically you have a predefined material here for the reference demo. It was just not mentioned what material it was. Sorry, this is not what I wanted. I wanted the thermal. I wanted the heat capacity. Sorry. So the heat capacity is around 300 joule per kilogram Kelvin. Thermal conductivity typically for PCB around this value, and the density is 1,800. Here for the demonstration, this will be pretty good. So now we have the material set up. We have assigned in which region it is defined. And that's about it. So we have two materials here. We can proceed to the next step, which is defining shared expressions. So we are going to make frequency sweeps, and we're also going to make resistance, like termination resistance sweeps. So we're going to define two quantities that have a default value. So for example, 10 gigahertz for the frequency, and also the resistance that we will use for termination. And this is going to have also a default value, 50 ohm. But we will sweep them, so we will override them later on. And these will now be available within the software anywhere for use. So this is done, so we can proceed to the next step, which is the physics definition. As you can see, we support all sorts of physics, and electromagnetic waves is just one of those. So you can do lots of things like computing capacitances, computing magnetic fields, doing like MEMS device simulation, also acoustics and whatnot. But here today it's about RF. So we're going to add the electromagnetic waves physics defined everywhere. And then we're going to assign now the boundary condition. So this is very easily done by invoking this plus button. So we can start with a perfect conductor condition. And what we will do is we will hide the air. We will add a region where this applies. So the track is considered here a perfect conductor. And then this, and then this, which is the ground, is also a perfect conductor. So that's about it. We can add lots of other things, such as the electric losses. Very easy. This would then be in the electric, and we could use a loss tangent, such as, for example, 1e minus 4. Next step, we need to drive this. You can do lots of things. For example, if you have an antenna, you can have an absorbing boundary and compute radiation pattern, but this is not what we're going to do now. What we're going to do, we're going to add the eigenmode port, which is how basically you might know it as a wave port. And we will define it on both sides. So we will have the input eigenmode port defined on the surface. So you can draw also a little surface around here. Here, it will be very accurate by just capturing the entire surface. And then you can tune it the way you want. But typically here, you just have one single QTEM mode that can propagate. So there's not much tuning needed. You can provide a target dielectric permittivity. And since there is only one mode, there's not much else to do. And then you can choose also a driving signal. So you could actually type sine 2 pi ft, sine 2 pi ft. So the frequency is known to the system because I've defined it. And you could add a phase shift if you want. So this works really well for phased array, for example. So here, the S parameters will be calibrated according to this phase. So here, sine 2 pi ft. So that's it. The other thing we need to do is on the other side, we will have to also define a wave port, eigenmode port here. And we select all the surfaces. And we do exactly the same. That's it. So sine 2 pi ft. And now we're done. There's nothing else to do. And we can proceed to the next step, which is simply running the simulation. So for that, you need a mesh. So we can use the default, works well. We're meshing it. Then we define a simulation. We associate the mesh to the simulation. We provide an input because here we will actually want to sweep over the frequency quantity. And this sweep will actually already show the first added value of running things in the cloud. That is being able to run a lot of sweeps and different runs at the same time. So when I ask to run a frequency sweep from 1 gigahertz to 10 gigahertz by 10 steps, so of 1 gigahertz, in a desktop computer, this would require to run serially all of these 10 steps. Here they will run actually on different hardware, all the 10 at the same time. So here it's a simple simulation. So it's okay that you have to wait a few minutes so the run is done. But this actually is very general, and it applies also to very complex simulation where you would actually have to wait days or hours before all the frequency points are simulated, or any other suite for that matter. So this gives for large simulation gives a guaranteed 10x speedup, and you can use 100, and then you're going to have a 100x speedup. So this is a trivial way to scale in the cloud. Now, what I will want to see here is the S parameters. So that's what I get. And if you want to visualize the field, then you would just select the electric field output here. And I will also have to tell it what type of analysis I want to do. I want to do a harmonics of frequency analysis. Which frequency? The one that I parameterize and I defined before. So the frequency frec here. And then we can don't have to, but we can dive a bit deeper in terms of hardware. So you can really run with any type of hardware you run. So if you need access to 1.6 terabytes of RAM for a large simulation, then you can run on 100 nodes of 1 core, for example. Here it's a small simulation, so we can just run with the most simple machine. And we're now all ready to go, if I didn't make any mistake. And soon we'll be able to see the S parameters of this device. And as you can see, all the jobs are starting at the same time. You can inspect each individual job. You can see that it has found one mode at each port, and it's already done. And in a few seconds now, we can visualize things. So now we can plot the S parameters, for example. So S11, S12, and possibly also the very typical S12 phase. And you can see that there's a line delay indeed. And actually it matches, of course, exactly what this benchmark online gives. And you can see that the S parameters are either 1 or 0. So the S11 is 0 and the S12 is 1 because everything goes through. So this concludes our first simulation. And the next simulation we could do now, and I just have to be a bit careful about the time, is illustrate a bit our lumped ports, because lumped ports are really the essential building blocks with eigenmode ports of RF simulations. So what we could do is I could deactivate now the eigenmode port. So the out eigenmode port, I keep the in active. This one is still active. This one is disabled. And what I'm going to do instead, I'm going to connect a resistive load at the end here. And I'm going to see like what is the load you have to take so that you have no reflection. Let's go for this. I will set up what we call a lump VI here, so a lumped port. So this was the other driven side, and this is where I set the lump port. And this is actually, I would say, a very convenient implementation of lump ports, because you can trivially use it to drive all sorts of waveguides, such as, for example, as we will see later, a coplanar waveguide, grounded or not. And it's really trivial to set up. So what you do is you define all the phase where you want to compute it. And typically what you are used to is probably defining just this surface and assuming that the electric field goes from top to bottom. But this neglects a lot of things like the fringing field. And so you will have like artificial reflection due to this. Here, this is not the case. Here, it's actually going to consider the fringing field by computing a pattern of electric field based on an electrostatic simulation. And this is really close to reality for like all practical applications at relatively low frequency. What you do next is then you're going to add a curve where you have a 1 volt for your electrostatic simulation. and a curve where you have a 0 volt for your electrostatic simulation. And this is the ground, and the other one is the 1 volt. And then what you can say is you can either drive or you can connect a circuit. And on the circuit, you can connect, basically, you can say that you have a resistor, capacitor, or inductor. And if I have my R resistance that I have defined before, then I can say that actually V is equal to Ri there. So I have a resistance lump connected here. And so I have a resistance there. So in terms of the current is related to the voltage by a resistance. And here I'm driving with a wave port. Let's see now how what you get when you do this. What I will do is I will still compute the S parameters. And we will see what S11 looks like as I sweep the resistance now. So let's sweep the resistance, and let's go, for example, from 0 to 60 ohm, and we want to run 40 simulations of that. Let's do 41. So we have, no, let's do 40 anyway. And yeah, that's about it. So let's run this. I hope I didn't forget anything. These live demos are the best thing to get demo effects. But you can see that all the jobs are starting at the same time. Again, you can see what's going on. And as they will finish, you will see here, you can see the data coming in. And your simulation will soon be available for visualizing the outputs. So S parameters, they're coming in. And this is what you get. So this is actually, again, still the same reference Microstrip waveguide. And you can see that you get actually a sharp, really close to 50 ohm, which is the actual value. And you get really a minus 41 dB match there. And this is really good, especially compared to these regular lump ports. If I would run a lump port, just selecting this surface here as the port, you would have much more artificial reflection. You wouldn't be able to get to minus 40 dB. So in that sense, it's really a good termination and it's really easy to set up. So this concludes now the second part of the demo. And I can go to the third live part of the demo, which is now see how much this guy heats up as we feed this 1 watt time average power through the wave port. We will keep the lump connected, so we will see how actually the device heats up based on the reflection. So for example, with pure reflection, you're going to have a standing wave, and you will see that the heat actually, it heats more at some places on the track than others. And we'll investigate that in just a second. So for that, I'm now doing a multi-physics simulation. What I need to do is something I already did. I need to provide the other properties, such as the density, the heat capacity, and the thermal conductivity, which, by the way, can all be anisotropic whatsoever. They can also be temperature dependent. So you could have epsilon that is temperature dependent if you want to, but not the case here. And then what we're going to do is, I will define another physics, heat solid. So that's the thermal conduction. And where does it apply? It applies in the dielectric. We have here a surface perfect conductor. So this one effectively doesn't have losses. For example, for superconducting devices, you shouldn't have that many losses in the tracks, but you might still have dielectric losses. So we'll just consider here the dielectric losses. And what's going to happen is we're going to define, as usually, a thermal conduction simulation, like a lot of our customers do quite routinely. So nothing fancy here. You define a thermal ground here, for example, with a reference temperature. Here it's relative, so you can consider that it's the temperature delta. And then the next thing we need to do is add a heat source. So it's going to be a volumetric heat source that depends on the electric field. And there's a formula for that you can easily check online on Wikipedia or whatsoever. You can also expect soon to be able to have a special interaction here for like dielectric heating. So you don't even need to write any equation. But for now, this is the formula. So it's the pulsation times the dielectric loss tangent. And then you multiply epsilon permittivity times E. That's the formula. Very simple. And you have it all set up. And now we can go to this simulation, which I will delete and I will redo because now it's a multi-physics simulation. What I want to do, and this is actually not such a trivial simulation, because the heating is actually a quadratic dependence on the electric field. So you have actually a constant heating plus some harmonics, which are negligible at 1 gigahertz. But we have, and I believe we're one of the few ones to have this technology, this harmonic balance method, which we can use conveniently here. And what it's going to do is going to just consider all the possible harmonics and the nonlinear effects. It's actually a frequency nonlinear analysis tool. So the fundamental frequency is FREC, and we are going to say that we want to consider the constant components of the field, as well as the real part and the imaginary part of the field at the fundamental frequency. So the temperature will have a constant component, and the RF part will have only like oscillating component 2 and 3. And that's about it. What we will want to say is we want still to do a resistance sweep from 0 to 60 by 40 steps. And what we want to do to see out is the temperature profile, for example, the constant part only, the only one that is non-zero here, only on the skin of where it's defined. So it's going to be the skin of the substrate. Now, one last thing we have to do, and this is only temporary, is that we have to go to the script, which allows me to introduce the script. So this is automatically generated based on everything I've done graphically. It's very short and concise, and you can tune it the way you want. And this is what I'm going to demonstrate just now. So the electric field won't have a constant component, so I can just remove it. And the temperature field won't have a component oscillating at the fundamental frequency, just a constant component. And we are all ready to go then. And I can just run the simulation. And I have to associate the mesh. And now I'm running the simulation. And again, as usual, I can also tune the hardware to, if we don't want to even wait a few seconds that the machine boots up, we just have instant start. You can see all the jobs starting as usually at the same time. And within no time, they will be all throwing out their temperature profile for each resistance. Now we can, we can inspect what's going on. So it's not essentially a nonlinear problem. You could just solve for the electric field and then for the thermal effect, but it's very general. So if you would have components that are actually temperature dependent, such as the electric permittivity, this would work out of the box. And now we're soon good to go to visualize the temperature profiles as soon as the simulation is wrapped up. Now let's visualize the temperature profile here. And we will be able to see for each resistance load, what is the temperature profile, I hope, if internet allows. Let's try for 10 seconds. If not, then I will jump to the last section, which is the hanger resonator simulation. But let's try again before. Well, I'll come back to it later. But we can go on to the hanger resonator demonstration. So one of the demos we have is this dielectric heating hanger resonator simulation. And this hanger resonator was obtained by importing a step file. So not drawn in the browser here. And I'm really sorry for this again. Right. All right, that's better. So, well, now that we're back here, let's investigate this one. So this is the heating due to the dielectric losses. And you can see that this is when you have a zero resistor at the end. So there's a perfect reflection and standing wave. And you can see that as you actually go towards the 50 ohm, well, you can actually visually see in the thermal profile that there is no more reflection. That's actually pretty funny to watch. But yeah, so this is actually the extra heating. So very small heating, like 350 microkelvin with the 1 watt that I used and with the electric permittivity that I used. But this concludes now this simulation. We can jump to the hanger resonator simulation, which I hope will display. But essentially, it's exactly the same. So a hanger resonator is a device used for filtering. It's in many ways similar to a stub filter, except that it's used typically here on semiconductor devices on the silicon substrate. And the setup is otherwise exactly the same. So you define exactly the same. And I hope I am able to show you a visualization of the outputs. Yes, so at least I can show you the hanger resonator. So this is it. You have a copper track here. This is actually a non-grounded coplanar waveguide. And I've used 2 wave ports, one on the left and one on the right. And then here I also assume a perfect conductor copper, and I define some dielectric losses. Eigenmode port in and out. I target a given effective permittivity. I also set up the thermal simulation, and we're then ready to go. And this one, as I said, I will not run it because I think I'm soon getting over time. But what I can do is show the plot of the maximum of the temperature versus frequency. So again, this was done by running all the simulations at the same time. And this starts to be actually more beneficial here because each one takes more than a few seconds. So this overall took 10 or 20 seconds, but simply because we could run all the simulations at the same time. And this is the profile of the max temperature. And if I want to show also the S parameters, so this is the S11, and this is the S12. So you clearly can see the filtering effects. Sorry, S11, S12. You can see that there is transmission. There's a here 27 gigahertz dip in the S12. And this dip actually corresponds to also a peak in temperature due to the electric losses. If I now show just the temperature, you can see that the temperature heating peaks at this resonance frequency, which is not very surprising. What we can do as well is visualize how the temperature profile looks like, and this will then conclude my section. So this is for the lowest frequency, not at the resonance. And then as I go closer to the resonance, you will see that the little hanger resonator heats up more on the hanger resonator part, which starts to have a larger electric field. And this concludes the simulations. So I will give it back to you, Jukka. Are you still there?
I'm still here. Thank you, Alex. So, as we have gone through the theory and now seen the actual live demonstrations, I'd actually like to pull you back on screen for the Q&A session. So indeed, it is Alex and I here to answer any questions you might have. We actually got plenty beforehand, so we'll start with those. But if any questions arose during the presentations, feel free to type them into the chat. So if we can get Alex back on screen, perhaps we can also get the video on. We could pull out a few questions from the forum. So the first question was that can Allsolve simulate RF propagation in different media, such as free space, dielectrics, and conductors?
That's a good question. So yes, it can. Actually, we have simulated everything from plain electromagnetic wave scattering with 40 million unknowns in air, and the interaction also with conductors. We also have done lots of antennas, such as dish antennas, for example, where you have radiation in air. And there's no limitation regarding this. And there's also no limitation regarding any geometrical shape. It's a finite element, and it supports kind of the most general method you can find.
All right. How about integration-wise? Can also be integrated with existing RF design and analysis tools?
Yeah, that's a good point too, especially very timely because we have released our first version of our API. So you don't have to necessarily use the graphical interface of the product. The algorithm are available for remote API access. And we're trialing it with already 2 customers. And this allows integration to your workflow, but also to any existing software. So it is not impossible that in the future, at some point, you start having more capabilities to run simulations in your favorite, let's say, PCB design tool, thanks to like integrations through APIs.
Right. How about it was a question, this general question on how long would you say it typically takes to get up and running with Allsolve as a new user?
I would say, and people will disagree, you are like very familiar with the software they use, but in all honesty, I think some of the existing tools, let's not be too general, some of the existing tools can be actually really difficult to use for a new user, as you mentioned, and also leading to a lot of wondering what you're actually doing and what sort of impedance you're actually measuring. And in that sense, I strongly believe Allsolve is an order of magnitude easier to use than what some people are used to. And I think we actually did a trial with a person that started to work at Quanscient, and within half an hour, that person was able to do already multi-physics simulations, although she had never used the tool. So I would say it's pretty good at that.
Right. Two questions. How about academic discounts? Are there any? I know for a fact that there are, but do you, Alex, have maybe some details on that?
Well, as you say, they are indeed um, academic discounts. Well, I guess it's pretty usual, and it is also our goal to provide the possibility in academia to have access to quality tools. Um, and this is why we offer academic discounts. And of course, we are also uh, understanding for longer contracts that the longer the contract, the more we can negotiate. Absolutely.
Yes, and last question regarding this the usage-based pricing, which might be new to some folks, actually many. So how does that compare to traditional software licensing? We already covered a few points, but in your own words, how would you frame it?
It's I think it's a game changer. I remember from my past times what you just mentioned, that there's a fight for licenses, which is inefficient, which actually even leads to people blocking licenses just to be sure they can keep access to it after lunch break. So it's very inefficient, very expensive, and also yeah. Yeah, expensive, inefficient, and like also it is a problem that you cannot even sometimes access the simulation results if you don't have the license, that you cannot even log into the graphical interface. And I think if you really want to allow larger scale adoption and taking advantage of the benefits of simulations, then I think the cloud-based licensing, capacity-based, sorry, is kind of the way to go. It's a big changer, and it's pretty new for the simulation industry, but it's gonna come. This is how I believe this is how it's gonna be, because it, we already see it in so many other tools. It's got to come one day. I see
All
also
right.
a lot of other questions on the chat. We maybe you had some more, but can variables be assigned to geometries? Yes, it's possible. So I didn't do it because I went straight for efficiency of demo. But in the shared expression, you can define, for example, the thickness or the width of the track, and then you can use it in the geometry. And then you can actually, for example, in the API, one of the first demos we have made was a stub filter, and we have run 10 different geometries parameterized on a given stub length or something like this. But yes, definitely. And it's done by defining shared expression that you can use throughout the code, throughout the software, and for example, also in the geometry editor. And the second question I see is, can you plot the magnitude of the electric field or magnetic field versus distance or depth inside of the electric material? Yes, we have specifically a function for that to plot along the line. And then you can render that as a plot, just like I showed.
Nice. In case of any other questions, we might not have time to answer now, but if there's anything, you can leave them as comments to the event right there, and we'll respond to them after the event. Or, of course, you can reach out to us directly, either myself or Alex on LinkedIn. But with that, let's wrap up the Q&A section. So thanks, first of all, for the awesome questions beforehand and here now live, and thank you, Alex, for the wonderful presentations.
It's my pleasure, and I believe we'll do more RF webinars, so we can also cover a bit more advanced cases.
Yes. Before we leave, let's do a quick conclusion on what we discussed here, what we saw here today, and leave you with the key takeaways. So, in the beginning, we covered the common challenges faced in RF design caused by basically limited computational capacity and software restrictions. The challenges we presented were limited design exploration, hindered collaboration, and complex and time consuming simulation setups. Now, through the live demonstration, we saw how Quanscient also addresses these challenges through, for one, the virtually unlimited computational resources, an unlimited number of licenses with every plan, which allows the parallel simulations, and the intuitive interface, making it easier to set up even these complex RF simulations. And I should say that it is contingent that you have decent internet connection at your office. So the key takeaways would be faster design cycles enabled by the, again, virtually unlimited computational resources and parallel simulations, as we again saw in today's demonstration. Increased innovation as a result of the ability to explore a wider range of design possibilities. Improved collaboration enabled by the unlimited number of licenses with every plan and the cloud-based nature of the platform itself. Reduced onboarding time and increased productivity through simplifying the setups, again, as seen in the presentation today. And finally, simply cost savings through eliminating the need for expensive hardware and software licenses, also reducing upfront costs and ongoing maintenance expenses. Now, as promised, we want to not only show and tell how cloud-based software can make your RF design faster, but to really allow you to test it to yourself. And for that reason, we're offering all of the webinar registrants, again, no matter if you're here live or watching the recording, a 7-day free trial with completely unrestricted access to the platform. This will allow you to import your models, play around with the capabilities, and really see the results for yourselves in your cases. Now, to get started with this trial, simply schedule a session with our CRO, Nicola, a very friendly fella who will first discuss your use case with you. So basically assess the compatibility of the problems you're solving and the issues you're facing, and take into consideration your existing workflows to not only establish whether Quanscient also would be a good fit for you, but to also get an idea of what to expect in terms of results, cost efficiency, onboarding times, etc. After you have a good idea of what the platform can do to you specifically, Nicola will also direct you to the most relevant resources so that you will get the most out of your trial. With that, I want to thank each and one of you for participating with us here today. and I hope you learned something new. Again, for the last time, if what you saw here was interesting to you and you'd want to have a discussion with Nicola to assess what Quanscient also could do to you specifically, you can scan the QR code or simply head over to the link on the screen to schedule the call. Thanks once again for joining, and have a great day. Bye.